Hello, everyone. First of all, I would like to thank the organizers for inviting me to present my work and share my insights on it. I am Simran Arora, and I'm a postdoc at YITP Kyoto University, Japan. This is my recent work, which I will be discussing today on interacting dark energy and dark matter models in the light of current observations. And these are my collaborators for this particular work. Let us start. So we all know about the evolution of the universe, starting from the Big Bang to the expansion and to the accelerated expansion of the universe. We know that there is some unknown form of energy which gives an evidence of accelerated expansion, which we call it as dark energy. So one of the successful models so far which explains dark energy is lambda CDM, which is a standard model. We name it as a standard model. This is the particular model which fits all observational data sets very well, right? But in the recent times, we know that there are some discrepancies, there are some problems with this model, which give us an open question whether do we need to go beyond the standard lambda CDM model or not. So, is there any way to go beyond this cosmological constant, right? People usually try to study different parameters. We try to constrain different parameters to study dark energy. So some of them are equation of state. We call it as W. So this is basically a Taylor series expansion around the redshift Z. So we try to constrain this equation of state parameters, which involves some of the parameters, which is W0, which is the constant, and WA, which is a first order term of this particular series. So we try to constrain these unknown parameters, and W0 basically gives an equation of state at present time, basically at Z is equals to 0, right? So we try to measure these parameters to study the behavior of the dark energy, right? Another parameter which is important, this parameter is usually studied when we study large scale structure of the universe, which we call it as S8 or sigma 8. This is very important in the structure formation. Another parameter which is important is rate of cosmic expansion, which we name is at h naught, which is Hubble constant. And h naught basically means the value of Hubble constant at redshift z, basically at present time. So this is a very important parameter for accelerated expansion. And another parameter which is also important is energy density today, which we call it as omega m. So we try to measure these parameters, but another question which arises is consistency, right? Our results, our models should be consistent. Right. Whenever we study some particular model, if there are two models which predict the same expansion history, so that may predict some different clustering growth rates, right? Or some other different parameters. So we need to be very consistent. The model should be very consistent when we use early or late universe analysis, right? It should give consistent results. So, though we know that lambda CDM is successful, there is one discrepancy which we face today is known as Hubble tension, right? So we know what is Hubble tension. So Hubble tension is basically different values of H naught, which comes from different data sets. One of the data set is CMB, Cosmic Microwave Background, given by Planck 2018. So this particular data, which is based on early universe, right, post recombination, pre-recombination data. So this data gives us the value of H naught is around 67.4. And another data which gives us the value of H naught, 73, is local distance ladder, which is a supernovae data calibrated by Cepheids. So we can see that there is a big gap between these two values. So there is a bridge, right? There is a bridge between these two values. This particular gap, we call it as attention. This gives us a tension, which we call it as Hubble tension. So what we do is we try to frame some models and we try to explain with certain analysis, a theoretical analysis or observational analysis, that how we can reduce this particular Hubble tension. Or it can be reduced at some sigma level when we use different combinations of data sets, right? We have now at present many different observational data sets. Maybe a Planck, supernovae data sets have different different data, such as Pantheon Plus, Days 5 year, Union 3, and many more. And also we have another early data set, we call it as BAO, baryon acoustic oscillations, right? So we have different set of data sets. So when we try to check different combinations of data sets to study this particular to constrain this particular h naught value, and we check whether this value this discrepancy can be reduced or not, right? This is one of the open questions and nowadays. So next comes, how do we measure it, or how do we see it, right? So as I explained, that different combinations of data give us different values of H naught. So we call it as direct or indirect. So direct and indirect. Direct means it is model independent. Basically, this all the supernovae data sets which are coming, they are model independent. They do not assume any model as a baseline model, right? So these are directly coming from the galaxies. And indirect means they are model dependent. They take lambda CDM as a base model, for example, CMB with Planck and BBN and stuff. So so there is a mismatch, right, between these values. So you can see the pink band, pink line, which is coming from the CMB, and this blue line, which is coming from the supernovae or shoes data. So there is a gap, right? We can clearly see a gap. And whenever we are getting new data sets, this gives us a high precision, right? Whenever new data set is coming, it is coming with improved precision. So when this is coming from the improved precision, so this errors become small, right? When error is becoming small, the values between H naught, the gap between this particular H naught is increasing day by day, which means the tension is getting worse, right? So we need to study whether there is a discrepancy, or there is a way to include some new physics, or there are some systematics in the data, right? So we need to study that. We try to study all those questions at present, right? Okay, so what are the theoretical insights we have so far? Maybe we need some new dynamical or phantom dark energy. So we need to look up of theories which are able to cross phantom divide, but in a stable way. That is, there should not be any instabilities, right, in the model. Also, we can introduce some complicated or scalar field Lagrangians, which can give some new insights into it, or non-minimal coupled scalar field. Or there may be some huge systematics in the data, in which we think that the tension is increasing, or we do not have any idea whether this would reduce or not. So we need to try certain techniques, theoretical or observational techniques, to study Hubble tension. Okay, so let us go for the work we have done. So we have considered here Einstein's scalar Gauss-Bonnet gravity, in which we have considered two scalar fields. One is phi and another is psi, where phi is acting as dark energy and the psi is acting as dark matter. G is a Gauss-Bonnet term, which is given by this particular expression, and these are the Lagrangian corresponding to phi and psi scalar field, and this is the interaction between these two scalar fields, right? So you can you know that, I mean, that phi is a dynamical variable which explains dark energy behavior. So it is controlled by kinetic term and the potential term. So corresponding fields have corresponding kinetic term and potential form corresponding to the respective fields, and this is one of the potential depending on both of the fields, which gives us an interaction between these two fields. These are the field equations for the scalar fields, and these are the energy momentum tensors for corresponding fields. So when we go for the FLRW metric, we have the equation of motions corresponding to the fields, corresponding to the system. So we have this particular equation for FLIW metric, and we can write corresponding densities for phi and psi. So rho phi, p phi, rho psi, and p psi. And we have included this interaction in the psi term, where psi is acting as dark matter. This is the Friedman equation we have. 3h squared is equals to rho phi plus rho psi, and depending on this particular f. Okay, I forgot to tell about f. Uh, this f is basically the coupling function with Gauss-Bonnet theory, Gauss-Bonnet term, right? So this is the f function, the derivative of f coming from there, with depending on phi and psi at the moment. But since it's a very complicated system, so we try to fix this f to be only a function of phi field. Next comes the continuity equation. In the continuity equation, we can see that there is a term which we say that this is responsible for the energy transfer between the two fields, right? So this term is given by phi dot W, derivative of W with respect to phi. W is a potential corresponding to phi and psi both, right? So this is the term which is an interaction term between the two fields, which is responsible for energy transfer between the two scalar fields. So when you have Q positive, energy flows from phi field to the psi field. So we can just reframe these equations. We can rewrite these equations in a certain form, which can give an effective pressure. So effective pressure is given by this particular expression, and we can define the equation of state corresponding to these two fields. So we can study this equation of state parameter and how does it behave in this cosmic system, right? Cosmological system. We can also define the total equation of state of the whole system, which is given by -1 -2 over 3 h dot over h square, which is as usual we study. And after that, since the Gauss-Bonnet coupling is coupled to the function f, so we have a tensor propagation speed, which is depending on f. So we define it by ct square is equals to 1 plus 8k square f double dot, 1 plus 8k square h dot. So this ct square, the sound speed, is already constrained by the gravitational waves, and which has a bound already in the literature given by this particular uh, expression, and it is always greater than zero, right? So we since this bound is very small, we in our analysis we used ct square equals to 1, right? So we imposed directly ct square equals to 1, and we have solved this particular equation, and we got a relation of f dot and f double dot in terms of scale factor a. Now, to study the system, we need some assumptions, right? To, as a whole, we need to study the evolution, the cosmological history for this system. So we need to choose some potentials for our study. So for this particular study, we have used the exponential potential V phi. We have used the potential corresponding to psi field as a power law, and the interaction term as this, where this zeta phi is a coupling function. So we can clearly see that there are some free parameters, and in our analysis, we try to constrain certain free parameters from the observational data. Again, we have xi phi, which is a coupling function in W phi psi. So we need to assume, because it's again an arbitrary function, so we need to assume zeta phi. So we have dynamical variables here. So these are the corresponding densities to the fluids, the normal fluids we have, baryons, radiation, and GB coupling. So we have a constraint equation again from the Friedman equation. This is the particular very important constraint we have. We can also find h dot over h square in terms of these dynamical variables. So next we find the autonomous dynamical system. So what we do, we differentiate all the dynamical variables with respect to e-fold number n, which is log a, and we frame a system x dash, y dash, z dash, and whatever the variables we have in our dynamical system. We have to differentiate all the variables, and we have to frame an autonomous system. So what we do next is we try to study this system numerically, right? Rather than we are not interested in studying the critical points and all those study. We want the observational study. So we try to solve this system numerically, and then try to constrain certain free parameters we have in this particular system using observational data. So we have studied the cosmological parameters for this system. So in this figure, we can clearly see that omega phi, which corresponds to the dark energy density, which at present it takes a value around 0.6 something, or 0. Yeah, near to 0.6, and at past it was 0. Similarly, you can clearly see the profile of dark matter, which is omega psi, and it takes a present value around 0.3. Since we have numerically solved the system, so we get the numerical behavior for each dynamical variables. Also, the Hubble parameter is fitting the data well for the particular model we consider. So these are the initial conditions we have used for getting this particular numerical behavior for this model, right? So what now this gives an idea that there is a proper cosmological evolution for the model, and what are the parameter ranges we could expect, or what are the priors we would give in our observational analysis for the free parameters we have in the model, right? The motive behind the numerical analysis was to get the priors for the unknown free parameters, which we could expect to give a proper cosmological evolution from the past to the present to the future. So what are the data we used? We used cosmic chronometers, which is a Hubble data. We also used different supernovae data, which is Pantheon Plus, Dacia 5. We also used day CBAO data, which is a second release, recent release data. We also used CMB compressed, basically a compressing the full Planck likelihood, which uses the shift parameter and acoustic scale. Another important data we used is Roman, which has not been yet disclosed, but we had a mock data from the collaborators, and it has around 20,000. 824 data points gathered from the Roman Space Telescope. So this is a very strong future data coming into the picture, and it also covers a redshift up to z equals to 3, and which might give something new, I mean, which might give something strong. So this is the mock data we have used so far, which is not the final data, but this is the mock data coming from the forthcoming Roman Space Telescope. So these are the observational analysis results we have. So we have constrained certain free parameters, and some of them are fixed because the values were so small. We need to fix it, and it do not affect the cosmic evolution. And the other parameters which might affect the cosmic evolution has been constrained by this particular combination of these data sets, right? So we have used basis basically means the combination of CC plus Daisy Bow plus Planck, and base was common in all the combinations, but we have used different supernovae. So one was Pantheon Plus, and the second was the Dacia 5, and the third was Raman. So we can clearly see that our model for in terms of H naught gives us almost similar values according to near to the Planck, which is the lambda CDM model coming from the Planck. And but there is a little hike when we use Roman data. So the value is going up to 70, and which is a very good sign. I mean, we can give some new insight. We can get some new insights from this particular combination and from this particular model. So maybe in the future, this Roman would give something new. So which we are just waiting for. So we can also see when we compare our model with lambda CDM, we can clearly see that in case of Roman data, the data is preferring the model we have considered uh, in this particular interacting scenario. We expect something new from the Roman, and maybe we need to study more on these type of models which can give some new insights. Thank you so much.